Okay, good. Now we're live. I had to restart the computer. So one of the things that we want to hopefully correct for the future is what I like to say is separate the haves and the have-nots. Now, that doesn't mean anything to you right now, but you don't know what your future is going to entail for yourself. Some of you are going to go into maybe some sort of business. Some of you are going to go and do mechanical work. Some of you are going to maybe be an electrician or a general laborer that requires a technical school degree. But whether you're doing any of those above, problem solving skills are always going to be an important part of the workforce. So hopefully when we see this, it will help you in your problem solving skills. That is our goal. And some of you, again, that maybe move off to college, what we want to say is separate the haves and the have-nots. What do we mean by that? The haves, those that can, uh, let's say, apply and receive scholarships. We call that free money. And the have-nots, we don't want to see you on the outside looking in. And if we're a little confused about that, how many of you follow NCAA basketball in March? You fill out your brackets, and then it's fun when you get started, and then it seems like 2 or 3 weeks later, it's kind of like, I don't have any teams left in there. But that happens. So what we mean by the outside looking in is some teams don't make that national tournament, and that's what we mean by the outside looking in. We don't want that for anyone in here, but sometimes that comes down to personal attitude, whether it's towards science or, I'm not saying work ethic, but we certainly want you to improve upon those skills. So there's your maybe a little pep talk for today. Because believe it or not, we do have your best interests looking out for you. Would you agree with that? This would be yes, and maybe there's some don't formulate an opinion, but it's always refreshing hearing back from former students saying, we're doing great in college. That happened again today, and that's always good news. That's what we want for you. Okay? So, when we look at these, you've read the problem, okay? The next thing that we suggest that you do, some of you can solve this without having to write all that information down, but that's maybe not to your best advice that you could follow. But typically, what we say, you've read the problem, what should you do next? Okay, so what do we know in this problem then? Okay, so the mass is what? What else do we know? Okay, so what might, okay, well, tell me the area, then we'll come back to this variable. Okay, now, some of you can look at this and not get confused by that because you're looking at your label, okay? But what could possibly happen when you look at this variable? You might, I'm not saying we get that confused with the acceleration, but it's possible because we know how do we calculate acceleration with what variable? That's meters per second squared. We know that this is an area, okay? So whether you choose to, if you want to put a line over the top or squiggle, that's entirely up to you. But you can keep it separate, okay? But we don't. That's what we don't want is plugging these variables in the wrong spot. What else do we know in this problem? Okay. And we got what? It's way over there. 101 something. 525 kilograms dash meter. And again, sometimes it's not going to tell you what the momentum is. You need, well, not need to, but we hope that you can recognize that by its label. Okay, what else do we know in this problem? Okay, Do we need to be more specific? Okay. And how would you're correct, but how do you know why are you right when you say the initial? Okay, so it was going a certain speed before impact, which was. Oh, right there. See, that's why we want you to get this setup in here so that you don't have to continually go looking through the problem. You have all the information presented to you right here. Okay, is there any other, yes, time. Tool time. No, okay, yeah. 0.60 seconds. Okay, so what's the question ultimately asking for? Okay, and we're just going to put a squiggle over the top so that we know that we're looking for pressure and not momentum. Um, there, not that you would do this, but for myself, before we go to church on Sunday morning, actually watch the show Sunday morning. It's on CBS. Not that you'd be tuning into that program, but did anybody happen to watch that on yesterday morning? Maybe your parents had it on, or for one reason or another, but they were showing a little bit of a preview on a movie coming out that there's some really good movies that even myself I'd want to go see. Something about possibly the current war, was one of Knives Out or something like that, and maybe. But okay, for some of you are going to know exactly what I'm talking about when I say Carroll Shelby. Carroll Shelby. Okay, how about 428 cubic inches of a Cobra Jet Mustang? Okay. So, how many Christian Bale fans, like Batman Begins, Batman Forever, and okay? So, but but Christian Bale is in this movie with I can't think of his name right now, but it's called Ford versus Ferrari. Okay, so when we talk about Ford, not that everyone's going to think of probably the Model T would be probably the first thing you might think of, but as far as sports cars are concerned, you wouldn't think of Ferrari, but the Mustang was Ford's best-selling sports car, and it was a muscle car too. And he had commissioned Carroll Shelby to design this race car to go up against. I don't know his first name, whatever, Ferrari. But that looks like an interesting movie that would be fun to go see, entertaining, and not only that, but one of the things that happens, I kind of thought about that with when you're talking about racing. I thought it was a general conception that a lot of people like going to races just to see the crashes. Is anyone here a racing fan? That whether it's NASCAR or I'm not myself, but I think there's some validity and a lot of science that goes involved into that. But one of the things that's what this problem's kind of based off of here is, as you can see, certain types of racing. So, what is it that we label pressure in? Does anyone know? Pascals. It's actually pascals, or if we're talking about newtons per meters, okay? So, and I'm going to make sense of this in just a moment. We know that work is measured in what, okay? So what happens is we know that forces are newtons and distance is going to be meters, so that when we talk about work, yes, it's measured in joules, but also a newton per meter is also considered as a joule, an amount of work that gets done. So when we look at this pressure, okay, what is the formula for pressure? So we know that pressure equals force divided by area. So when you look at this, if you have a Newton over a centimeter squared or a meter squared, we're not too concerned about that. We usually just make the conversions. If it's in meters squared, leave it meter squared. If it's in centimeters squared, leave it in centimeters squared. Because once you have that here, we know that any variable that has a square or an exponent of 2, we know we're labeling it as a what? If you take length times width, we know that that's an area. Okay? So whether you have newtons over an area is going to be measured in pascals. You can do that as well. If you labeled work as a newton per meter, you would be right, because that's what makes up that work formula. So if you were to label pressure as a newton per meter squared, that's comparable to pascals as well. Okay. So now that we have this down here, what do you think is our next step? So to solve for pressure, we need to know the force, because we've got the area. So you tell me, can we calculate the force with the area, or excuse me, can we calculate the force with the information that we have right now? And the answer would be no. Okay, so if we're looking for this, we've got the area, but we need to be able to find the force. So, and from prior knowledge, what does force equal? Okay, well, we've got a mass, okay, so we know we got to find that force. And we've got our mass, which is 1770, okay, but we're missing what you correctly identified as the acceleration. Okay, and a lot of you have said that we kind of struggle with some of these problems. That's why we go over these, so that hopefully we get better at this problem solving. So we need to find this acceleration. That's a problem right now. Okay, well, what does acceleration equal? From way back in September. Okay, so final velocity minus initial velocity divided by time. Well, we're getting a little closer, because we need to know 3 of these 4 variables. We've got the time, and we've got the initial velocity, but we don't have that final velocity. But can we solve for that final velocity? Some of you are nodding your heads yes. How would you go about doing that? Well, that would be true, but we don't have the distance. But with this information, how can we solve for this guy? Okay, so we have the momentum, which is 101,525, equals, according to that formula, mass times final velocity. Well, we've got the mass, 1770, times VF. Those would equal one another. Okay? So, someone please divide 101,525 by 1770. Geez, I didn't think it was going to... I just made this problem up. Okay, 57. Is that what someone else got? 57? Okay. Okay. 57.36. Okay. Well, now we can put that into this formula now, 57.36. 57.36 minus 70, okay, divided by 0.60, okay? So let's go ahead and subtract those. Does anyone see the problem that's coming up here? Yeah. Okay, that wasn't my intentions, but you're going where the numbers lead you, okay? So you get, what was it? You say 12.64. Okay, so acceleration equals 12.64. Okay, I understand it's negative. I get that, but I didn't realize that was going to have a number smaller than 70. Okay. Okay. So, oh, 2.17. Okay, but we're going to leave that whatever it is. 2.17, 2.98, 21. Okay. Again, we're solving this with the numbers you have. I just made this problem up, so sometimes it doesn't work out how you envision. But anyway, now that we've got the acceleration, what can you take this 21 times? We can take it times the mass, and that gives you a what? And that gives you a force. So force equals 1770 times what we just calculated, 21.17. So our force is approximately what? Repeat that again. And that is newtons. Okay? So now, we're going to take that number and divide it by what to get our pressure? 4.40. Okay? And that will give you your pressure. Okay? Left outside. Are we good? Left middle. Middle. Right middle. Right middle. Okay, sorry. Right outside. Right outside. Right outside. Okay, if you're telling me that we're following this, we're moving on. Okay, asked and answered. All right, so as we look at this week, I've got some papers here to hand out for you. I've got another one tomorrow, but one of the things I want you to note or look at, yes, there's a couple of assignments on the board, but does it say that they're due on Wednesday? No. Does it say that they're due on Thursday? No. So it's not like if you take it home and finish it, fine. If you don't take it home tonight and finish it, that's fine too. Okay? So my point is we've got time to work on that this week because as you can see from the problems that you've gone through and solved so far this semester, is this one of the hardest one that you think you've had to solve? Yes. So I think you'd agree that some of these, they're becoming more and more complex. And I get that. We're saying, well, we don't understand how to keep moving forward. But what can you do to help yourself out? Watch the Science Channel. What else can you do? You can come in. You can ask myself. You can, before or after school, talk to an upperclassman. They can probably point you in the right direction. But that is one of the things you have to take initiative for. All right, so we will catch up to you next time.